This video explains how to design a digital circuit that runs high-quality, high-speed vision AI by connecting only basic logic elements such as adders and multipliers. The AI circuit designed in this video is the same AI solution demonstrated in previous videos posted on this channel. Familiarity with the Verilog hardware design language is not necessarily required to understand this video. But if you are familiar with the language, referencing the Verilog source code for this design will help you understand the hardware architecture described in this video. All of the Verilog source code used in this design is publicly available. In addition, using the Zinc AI development kit, you can hardware simulate this design, or place and root and run it on a development board. So, by following this video, you can start from the hardware source code, create a hardware binary, run it on your development board, connect your laptop's desktop to the board's video input, and do some fun video AI tests, and you can even use it to develop various AI application services yourself. The architecture of this design is conceptually simple and completely different from the matrix-based general-purpose architectures commonly used elsewhere, such as GPUs and NPUs. It is a special-purpose architecture dedicated to deep learning computation, achieving high speed and high accuracy, even with a small amount of resources. AMD, the leader in the FPGA industry, has discontinued support for the Vetus AI solution for the Zinc 7020 FPGA chip due to the limited hardware resources of this chip. But as demonstrated in the previous video of this channel, the design presented here can run vision AI algorithms at high speed on the same Zinc 7020 and can be applied to various applications. On the other hand, Jetson Nano, an embedded GPU chipboard, has 512 gigaflops of computational resources. Our design achieves similar AI performance to Jetson Nano using only 45 gigaflops of resources. This means that we achieve similar performance with less than a tenth of the resources. This proves that this hardware design is very efficient compared to existing designs. The ultimate goal of this video is not to simply describe one AI design, but to share a new AI hardware design methodology. The potential of such a design approach lies not only in executing AI computations on small chips, but also in executing very large AI computations with less power and space, as is increasingly required. I am sure it will be an interesting topic for anyone interested in AI hardware or students learning digital circuit design. This video will proceed as follows. First, we will explain the input-output interface of the system, describe the convolutional neural network, which is the technical background of AI hardware, and then look at what efficiency means in AI hardware. Then, after setting our design goals, we will explain our approach for efficient hardware design, the problems involved, and how to solve them. Then, as the main topic, we will explain the components of the designed system, how it works, and how efficient it is compared to the efficiency goal. Finally, we will explain the structure of the source code. This may be a bit of a technically heavy topic, but please take a quick look at it, and if you're interested, take your time and read through it. If there's anything you don't understand, please leave a comment and I'll do my best to explain it. The AI circuit described in this video can in principle compute a variety of AI algorithms, including classification and object detection. But for the sake of explanatory convenience, this video focuses mainly on the classification algorithm. This circuit receives frame images continuously from the HDMI input, recognizes which object the image belongs to, continuously outputs the recognition results, and overlays the results on the HDMI output. The computation circuit operates in a standalone manner and is completely CPU independent. When the CPU informs the hardware circuit of the input image address, the computation circuit starts the computation, and the CPU does not participate in the computation at all until it is completed. Therefore, the CPU is free to do other things, and the AI circuitry can run at a constant speed regardless of the CPU load. In the recognition process, the computational circuit uses parameter data generated in advance through the deep learning training process. This data contains knowledge about the recognition targets, There is no need to modify the computational circuit even if the recognition target changes, and just by replacing the parameter data, the circuit can be used for various purposes, such as classifying animals, recognizing gender and age, or recognizing whether there are defective products in a factory. Most AI algorithms use convolutional neural networks as their framework. Convolutional neural networks perform convolution operation on input images to create multiple output images, and then use these output images as inputs again to create the next output images, repeating the process until the final result is derived. The images generated during this process are also called feature maps. In this process, a single step of computing, the output feature maps for the given input, feature maps is called a convolutional layer. In general, a single convolutional layer performs the following computation. This formula may look complicated, but don't panic. The important thing to note about this formula is that most of the calculations are multiplying the elements of the input feature map and the parameter data, and then adding the products. Simple multiplications and additions are the basis of this convolution computation. The convolution equation described above can be visualized by drawing it as a data flow graph as follows. In each input image, each data point in the k by k receptive field becomes an input to a multiplication node, and the other inputs of those multiplication nodes are connected to a weight value unique to each k by k point. The results of all multiplication nodes are summed in the summation node, and the summation results calculated in the same way in all input images are summed again in the summation node to derive a single value. This value becomes one value of the output image after passing through a simple activation function node. This process is repeated until the receptive field scans all parts of the input images, and all values of the output image are computed. This figure is simplified for convenience, but the actual structure is much larger. In the case of our classification algorithm, the number of input and output feature maps to be calculated in each of the 53 convolutional layers and the number of required multiplications are as shown in this table. The 34th layer of the classification neural network, for example, has 136 input feature maps, 816 output feature maps, and a total of 22 million multiplications and additions, which is a huge amount of calculation. The entire classification algorithm requires approximately 580 million multiplications and the same number of additions. So how can we design digital circuits that can perform such massive computation at a high speed using limited resources like the Zinc 7020 FPGA has? To achieve this, we need to maximize the computational efficiency of the circuit so that we can perform a large amount of computation using a small amount of resources. To understand the key factors in the efficiency of a computational circuit, let's imagine an ideal AI computational circuit that is extremely efficient and impossible to implement. Most AI algorithms require a fixed amount of multiplications. For example, our classification algorithm requires 580 million multiplications, as mentioned earlier, and our object detection algorithm requires 1.23 billion multiplications. This is an inherent property of the algorithm and is stated in the papers that publish each algorithm. Note that an equal number of additions are also required along with the multiplications, but adders require very little resources compared to multipliers, so they can be conveniently ignored without obscuring the overall point. Efficiency is the overall AI computation speed relative to the resources used, so we want to reduce the invested resources as much as possible to increase the efficiency. However, we cannot eliminate the multipliers because the AI algorithm can never produce a result until the multipliers perform a given number of calculations. Therefore, an ideal AI circuit we can imagine is one where the circuit consists solely of multipliers, and all multipliers produce results continuously at peak speed without a break during the entire computation period. An ideal computational circuit consisting of 128 multipliers would look like this. In this circuit, all resources are used to implement the multipliers, and all multipliers are operating without any idle time. What's interesting is that once the number and speed of the multipliers are determined, the maximum AI algorithm computation speed that the circuit can compute is also determined. For example, imagine a computation circuit consisting of 128 multipliers operating at 170 MHz. Computing a classification algorithm that requires 580 million multiplications for one image. It is theoretically impossible for this circuit to compute the classification algorithm faster than 37.5 times per second. This is because the maximum number of multiplications that all 128 multipliers can calculate in 1 second is 21.8 billion, and one image requires 580 million multiplications, and 21.8 billion divided by 0.58 billion gives 37.5 images per second. If you want to increase the maximum speed further, you will inevitably need to use more multipliers or faster ones. Obviously, since all the multipliers are absolutely necessary and work at full speed, no circuit can be more efficient than this, assuming that the efficiency of the available multipliers is the same across the system. Also, this circuit is incomplete and infeasible to work because this algorithm requires not only multiplications but also many other computations, either explicit or implicit, and circuits that perform other computations would be needed to properly compute the algorithm. Furthermore, this circuit does not even have a circuit to transmit data to and from the multipliers. In reality, it is difficult to fully utilize all the multipliers, and a significant amount of resources must be used for components other than the multipliers. Although this ideal circuit is impossible to implement, if we design it as close as possible to this circuit, we can achieve high computational efficiency. For this reason, we set our design goals to minimize resources spent on purposes other than the multipliers and maximize the utilization of the multipliers. To achieve the first goal, we need to minimize the circuitry added to the multiplier. If we have to add additional resources to do something technically fancy, we will lose efficiency. To achieve the second goal, we need to make the multipliers work continuously, not just at certain moments, but continuously throughout the entire computation cycle. If the multipliers have to stop in the middle to do some additional work, such as moving data in memory or synchronizing data, we will lose efficiency even more. So how can we design a circuit that maximizes the utilization of multipliers? Our approach is to design them in the same structure as the data flow diagram shown above. Each multiplication node is converted into a multiplier, and each summation node is converted into a tree of adders, and the entire circuit is designed as a single pipeline circuit that is synchronized to the system clock. If we can provide continuous input data to this circuit, all the arithmetic operators can be continuously provided with the input data necessary for their calculations, so that all the arithmetic operators in the circuit can perform calculations continuously. This method is in contrast to existing general-purpose computational architectures that fix the hardware structure regardless of the structure of the algorithm and convert the algorithm to fit the hardware architecture and compute. In these architectures, inefficiency mainly arises from the difference between the hardware structure and the algorithm structure. However, if the hardware architecture is designed to fit the structure of the algorithm from the beginning, the two structures can be perfectly matched without a separate mapping process, thereby eliminating idle computational resources and maximizing efficiency. This is like connecting the production line in a factory in the same way as the workflow chart and supplying materials all day long, so that all workers and machines work without stopping. However, this approach comes with several challenges that need to be addressed. First, as mentioned earlier, the data flow diagram is huge in scale, and the size of each layer is different, so it is impossible to convert the entire data flow diagram into a single hardware circuit. Therefore, scalability is required to handle a large and variable computational demand with a single fixed hardware. The second problem occurs when k is greater than 1, that is, in the case of 3 times 3 or 5 times 5 convolutions. In this case, k by k data from the feature map must be read simultaneously for each clock cycle, but the locations of the data are scattered within the plane space of the input image, making it very difficult to simply distribute them to multiple memories and read them. Since K by K data must be read simultaneously for each clock cycle, we can think of a method to store them in different memories and read them simultaneously. But data items of a specific feature map cannot be fixed in one memory because their locations within the receptive field move for each clock cycle. To solve this, we may need to use very high-speed memories or store duplicate copies of the data in multiple memories, which is inefficient. In addition, in cases where it is unavoidable to read multiple receptive fields simultaneously, the amount of data that must be read simultaneously from memory per clock cycle may increase rapidly, making it impossible to process with the limited memory data rate. Third, the multiplier input must be provided without interruption even when the convolutional layer is switched. To do this, the computational result of one convolutional layer must be immediately available as input data for the next layer. If additional memory operations are required in the middle, data cannot be supplied to the multipliers during that time. So the multiplication circuit must temporarily stop calculating, which results in a decrease in the efficiency of the entire system. Fourth, although the computational circuit is fixed as a hardware circuit, it should be able to execute various types of algorithms with the same circuit, and each algorithm consists of a large number of convolutional layers, each with different computational characteristics, such as the size of input-output feature maps, k-value, stride and activation function, global average pooling, etc. Therefore, the system needs a mechanism that can process such computational requirements in an orderly manner. Our solution to the first problem is as follows. We fix the total number of physical multipliers to a specific number, n. We divide the total number of multiplications required in each convolutional layer into blocks of size n, compute them block by block, and then sequentially add up the results in the accumulator at the end of the adder tree. This method enables computation with fixed-size hardware even when the number of input-output feature maps is large and variable. To solve the second problem, we use a special circuit called a receptor unit. The receptor unit allows a continuous supply of large amounts of input data to the computational circuit by reducing the required memory access rate to 1k squared. The circuit of the receptor unit is implemented as an array of shift registers, and by passing the data input one by one for each clock cycle through the array, k by k sized view of the feature map is formed, allowing multiple k by k outputs to be output simultaneously for each clock cycle. Please note that in this procedure there is no interruption in the data supply, even during the transition phase between the end of one map and the start of the next map. The third problem is solved by using a special memory circuit called a network unit. The network unit consists of a large number of small memories and uses a switching circuit that operates by a control signal to enable the data stored as output in the previous convolutional layer to be provided as input data directly in the next layer. By using network units, no additional memory operations are required when switching convolutional layers, so data can be continuously supplied to the computational circuit, thereby maintaining high computation efficiency. The solution to the fourth problem is to design all computational circuits to be able to change the shape according to the control signals, and to provide the appropriate control signals at the beginning of each convolutional layer, so that a single circuit can compute various types of convolutional neural networks. These control signals contain all the signals necessary to control the circuit according to the computational characteristics of each convolutional layer, such as the length of the iteration loop, the memory read start address, the write start address, and the k-value. The control signals are defined on a per-layer basis, and the entire control data is called the Stage Operation Table, SOT. This SOT defines the architecture of the convolution algorithm, and by changing the contents of this table, multiple different convolution algorithms can be computed with the same hardware circuit. This SOT table is not only programmable, but is also loaded into the hardware just before computation, along with the parameter file. Therefore, there is no limit to the number of convolution algorithms that can be computed, and it provides a general-purpose architecture that can compute various algorithms depending on the contents of the parameter file. Now, with this technical background in hand, we will explain the composition of our design, adding units one by one from the blank space. First, the synapse unit, also known as SNU, is a unit consisting of 128 16-bit floating point multipliers. The two inputs and one output of each multiplier become the inputs and outputs of the unit. The SNU has a very simple structure, but it is the unit that takes up the most resources in the entire system, because the implementation of each multiplier requires much more resources than other parts. The multipliers are fixed firmly in the circuit like pillars of a building, and all other logic in the system works to create an environment in which these multipliers can work continuously without idle clock cycles. The second unit is the dendrite unit, DU. It sums the outputs of the SNU. This unit consists of several adder trees and the same number of DU tips. The DU tips are connected to the end of the adder trees and store the summation results and accumulate them with a time difference. The number of inputs to the adder trees used is controlled by a control signal that varies depending on the type of convolutional layer. The third is the soma unit, or SU. The SU is connected to the DU and performs simple functions such as bias calculation, activation function, etc. The fourth unit, the network unit, or NU, provides feature map data to the computation circuit and simultaneously stores the computed feature maps. It consists of a total of 32 small block memories and can output up to 16 data simultaneously per clock cycle and store up to 8 data. The total capacity of the block memories in the Zinc 7020 FPGA chip is only 560 kilobytes, which is much smaller than the size of the feature map that must be read and written when computing each convolutional layer. Therefore, the entire feature map cannot be stored at once, and partial feature map data is periodically read or stored from a large capacity DDR memory. The fifth unit, the receptor unit, is used when k is greater than 1 and reads 1 data per clock cycle from the NU and outputs k times k data. This unit has a total of 4 receptor circuits and can produce up to 36 data per clock cycle when calculating a 3x3 convolution, for example. For a 1x1 convolution layer, the receptor unit is not used, and 16 data per clock cycle are fed directly from the NU to the SNU. The softmax part performs the softmax calculation that occurs in the last step of the classification algorithm. Here, I will briefly explain the entire computation process. Outside the deep learning computation circuit, the HDMI circuit resizes each HDMI video frame to 224 by 224 pixel image and stores them in DDR memory. Before starting the computation, the CPU uploads the contents of the parameter file to DDR memory and commands the control unit to start the computation. When computation starts, the CU reads the SOT data included in the parameter data from the DDR memory, stores it in the CU, and operates the computation circuit to sequentially compute from the first layer based on the computation order of the convolutional layers specified in the SOT. The computation circuit sequentially computes the convolutional layers specified in the SOT one layer at a time. If this layer is a 1x1 convolutional layer, it is processed as follows. In this case, the computation circuit simultaneously reads 16 data, one from each of the 16 input feature maps, per clock cycle from the NU, calculates 8 output feature map data, and then stores them in the NU simultaneously. NU continuously fetches 16 data per clock cycle from the feature maps stored in the previous layer and sends them to the RU. RU replicates this data 8 times and sends 128 data to SNU every clock cycle. After calculating the products in SNU, DU adds up the groups of 16 and accumulates the 8 sum values in the DU tip. In the loop that processes the last input feature map, the sum values of the DU tip are sent to the SU to calculate the bias and activation functions and then stored back in the NU. In this process, all data flows in the form of a continuous stream, so the computation circuit can perform computation continuously without stopping. When reaching the last convolutional layer, where n is the number of objects to be recognized, n data are calculated in SU and sent to the softmax part, where the softmax equation is calculated and the object with the highest probability is picked as the result value of this classification algorithm. Once the computation for one image frame is complete, the above process is repeated using the most recently saved input image. This video shows the flow of data within the computation circuit. It is noteworthy that the SNU, which has the most resources, operates continuously without break. Now, let's measure the multiplier utilization of this circuit. First, we need to measure how many clock cycles the entire computation took. As explained in other demo videos on this channel, when running a classification algorithm with a zinc board, turning on the SW0 switch on the board and connecting to the serial port outputs the following report. The report shows that it took approximately 6.9 million clock cycles to recognize a single image. The maximum number of multiplications that all 128 multipliers can compute during this time is 6.9 million times 128, or 879 million. Also, as explained earlier, the actual computed effective multiplication amount is 580 million, which is the computational requirement for this classification algorithm. So the efficiency of the multiplier is 580 million divided by 879 million, or 66%. For the object detection algorithm, the following results were obtained. According to this report, it took about 11.8 million clock cycles to recognize one image, so the maximum number of multiplications that all 128 multipliers can calculate during this time is 11.8 million times 128, which is 1.51 billion. Also, the actual effective calculation amounts to 1.23 billion, which is the calculation requirement for this object detection algorithm. Therefore, the efficiency of the multipliers is 81.5%, which is 1.23 billion divided by 1.51 billion. Let's analyze why the multipliers were not utilized 100% in the case of object detection computation. Since only a part of the multipliers could be used when calculating 3 times 3 convolution, there were overheads. Also, when calculating 1 times 1 convolution layers, fragmentation overheads occurred due to the remaining pieces at the end when dividing the multiplications on the data flow graph by 128. The combined overhead of these two was calculated to be approximately 9.7%. In addition, an overhead of approximately 8% occurred while waiting for data when accessing DDR memory. As a result, the circuit achieves an effective multiplication rate of 18.4 billion, or 81.5% of the hardware resources, with a peak multiplication rate of only 22.6 billion per second. Considering that recent NPUs generally have resources of several tera operations per second, this design achieves good performance while using extremely few resources. This shows the potential to create NPUs that are much smaller than they are now, or to create NPUs with powerful performance in the same chip size. This design is mostly written in System Verilog, and the source code corresponding to each unit in the circuit is shown in the table. In the next video on this channel, I will show you how to place and route and package Verilog source code with Vivado software to run AI algorithms on a Zinc FPGA board and recognize HDMI video at high speed. In the video, we have explained how to design a high-performance AI vision chip using only basic components such as multipliers and adders. This design was able to achieve high computational efficiency by applying a design architecture called Neuron Machine, which directly reflects the structure of the calculation formula into the circuit design. This architecture can be effectively applied to algorithms that cannot be efficiently calculated with existing systolic array-based designs, especially those that depart from matrix calculation formulas. If you fully understand the content of this video, You may agree that the efficiency of this system is approaching the optimal efficiency that cannot be improved any further from the perspective of pure computation architecture. The binary of the system developed here has already been released on this channel, and you can run it right away if you have an FPGA board. You can also analyze the content of this video through the hardware source code released on Github. If you purchase a low-cost AI development board, you can implement the system binary directly from the source code and port it to other hardware platforms. We are always ready to help you. For example, we can help you with your extremely efficient, large-scale chip development project or with AI design training for developers. Please let us know at any time. Thank you for watching.